A nice application of series is, and in particular geometric series, is in understanding repeating decimals. So decimal is repeating if it finishes with a pattern that keeps repeating forever. So a sequence of digits that goes on forever. So you probably know that any rational number, any fraction, its decimal expansion is repeating or ending, terminating. So the way to get the decimal expansion of a fraction is by long division. So suppose I here have an example, 22 over 7. 22 over 7, if I want to express it as a decimal, I start by dividing 22 by 7. Long division, 22 by 7 gives 3, and the remainder of 1. Because 3 times 7 is 21, I get to 1. And then I drop a 0, because the remainder is not 0, so I drop a 0 after the decimal point. I get 10, divide 10 by 7, I get 1, and the remainder of 3, because 1 times 7 is 7. 10 minus 7 is 3, drop another 0, I get 30, 30 divided by 7 is 4, remainder is 2, because 4 times 7 is 28, you subtract 28 from 30, you get 2, you drop a 0, 20 divided by 7, you get 20 divided by 7, you get 2, 2 times 7 is 14, you have a remainder of 6, you take 60 divided by 7, you get 60 divided by 7, you get 8, because 8 times 7 gives you 56, and this is, so you have 8 sevens and 60 with a remainder of 4. Then 40 times 7, we're not done. 40 times 7 gives you, divided by 7 is 5 with a remainder of 5, because 5 times 7 is 35. You subtract 35 from 40, you get 5, and you dropped a 0, another 0, you get a 50. 50 divided by 7 is equal to 7. And 7 by 7 is 49, and then you get the remainder is 1. The remainder is 1, as you started here with a remainder of 1, you got back to 1, so it means that this sequence will repeat again, and these results will repeat again, and you'll get 1, 4, 2, 8, 5, 7, 1. And 1, 4, 2, 8, 5, 7, 1, and so on. So you get so that means that the decimal expansion of 22 over 7 is 3.142857 repeated. And of course, a pattern has to repeat because like the remainders of the possible remainders for division by 7 are going to be either 0, 1, 2, 3, 4, 5, 6. So at one point you're bound to repeat one of the remainders. One of the remainders will reappear again. Like you have a remainder of 1 and it reappeared here again, and once the remainder appears, the whole sequence repeats and the whole result repeats. Okay, so this is the process of converting from a fraction to finding its decimal expansion. But we're interested here for series. We're interested in the opposite process. Suppose I start with a decimal expansion and I want to find the fraction that it represents, its equivalent fraction. So how would I do that? So I start with this simple example, with the example of 0.333 forever, yeah? Or 0.3 with a bar. When we put a bar over the digits, means that this digit repeats forever. So probably all of you should know that this is the decimal expansion of 1/3. But suppose I don't know that and I want to find this myself. How can I find this myself? Well, I have to understand what is the meaning of this decimal expansion. This decimal expansion is actually an infinite series, because this is 0.3, right, plus 0.03 plus 0.003 plus etc. And you can rewrite it without each decimal here as a fraction. So this is 3 over 10 plus 3 over 100 plus 3 over 1000 plus goes on forever. So not only is it an infinite series, it's a geometric series. Why? Because if you can see that, you can factor out the first term from the whole series. Then you're left with 1 plus 1 over 10 plus 1 over 100, etc. So this is 3 over 10 times 1 plus 1 over 10 plus 1 over 10 squared plus 1 over 10 cubed, a geometric series. And since it is geometric series, we can use the formula for the sum of a geometric series, which says that, again, the formula is sum from n equals 0 to infinity. ARn is a over 1 minus r. So the sum here will be 3 over 10, my a, and this is my a, and 1 over 10 is my r. So times 1 over 1 minus 1 over 10. So this is 3 over 10 times 1 over 9 over 10, which the 10 cancel with the 10. And this simplifies to 3 over 9 or 1/3. Okay, so we got our result, which we probably know for this fraction, for this decimal, but this is what we not only got the result, we've seen what method we will use to find the equivalent fraction to another repeating decimal. Yeah? So this is, so if we have if we look at the second example here, 0.32 repeating, so this is 0.32, 32, 32, etc. We want to find the equivalent fraction. This is equivalent to a fraction. It's not an irrational number, it's a rational number because it has this repeating pattern. So we first can write this as 32 over 100 plus 32 over 100 squared plus 32 over 100 cubed, etc. Because this is 0.32 plus 0.0032 plus 0.000032. So 32 over 100. This is not 10 squared, sorry, this is 100 squared, because you have here 4 decimal places, and this is 100 cubed, 6 decimal places, etc. Yes. So here I'm decomposing this as 0.32 plus 0.0032 plus 0.000032, etc. Okay. Again, this is a geometric series. You can see it more clearly if you factor out the leading term, take out the a, 32 over 100, then you're left with 1 plus 1 over 100, because this is 32 over 100 squared, plus 1 over 100 squared, etc. So this is my a is 32 over 100, and my r is 1 over 100. So if I use the formula for the sum of a geometric series, r of course is less than 1 in absolute value, so this formula is valid. So I get 32 over 100 times 1 over 1 minus 1 over 100. So this is 32 over 100 times 1 over 99 over 100. So you get 100 cancel with this 100 cancel with this 100, and you get our answer, which is 32 over 99. So this decimal here, our decimal is expansion, or this is the decimal expansion of 32 over 99. This decimal expansion represents this fraction, 32 over 99. Okay. Okay, so our another example, the third example is the following. Suppose sometimes the decimal expansion has a non-repeating part. Like here, this decimal expansion starts with a non-repeating part. 33.7. So I'm going to rewrite it here. In this example, I have 3.7, 2, and the bar just above the 2. So this is means that it's 3.7222 forever. So to deal with these fractions, first you take the non-repeating part by itself. So 3.7. So you write this as 3.7 plus 0.0222. 3.7, you can write it as a fraction, 37 without the decimal, 37 over 10. And this repeating part is what you write is 0.02 plus 0.02. That will give you the infinite geometric series. Okay. So you get 37 over 10, and this is 2 over 100 plus 2 over 100 plus 2 over 1000 plus 2 over 10,000, etc. Okay. So this is 37 over 10, and this is geometric series. Factor out the 2 over the first term. This part is the geometric part. Factor out the 2 over 100, and then you're left with 1 plus 1 over 10 plus 1 over 100, etc. So this here you have R is 1 over 10, and A is 2, this is A, 2 over 100. Okay, so I continue up here because I don't have space, and so continuing this, you get 37 over 10 plus, you need to sum this geometric series, so 2 over 100 times 1 over 1 minus 1 over 10, so 37 over 10 plus 2 over 100, 1 minus 1 over 10. So this is again, we just did it here. This is 1 over 9 over 10. So this is here 1 over 9 over 10. So the 10 reduces the 100 to 10 times 9, so you get 2 over 90. So 37 over 10 plus 2 over 90. And you can bring into the common denominator, and you'll get, I believe, 335 over 90, which is not reduced. Reducing this to lowest terms will give you 67 over 18. So the final answer, the fraction in reduced terms, in lowest terms, the reduced fraction in lowest terms, that's represented by whose decimal expansion is 3.72222 forever, is 67 over 18, and we found that by using the formula for the sum of a geometric series.